be an overview on some algorithms that are implemented for the advisors mission. So we've had probably, most of you have probably seen a few presentations about things we're doing in advisors. This will be a deeper dive into some of the algorithms that are useful in making advisors amenable to applying the fancy control algorithms we have, fancy or simple control algorithms we have developed and are using, as well as ensuring safety of the spacecraft and advisors formation and how we predict collisions between them or potential collisions and safe violations. But this will mostly be focused on, just ignore it. So this will be applicable to spacecraft, which are smaller, meaning limited propulsion capabilities and processing capabilities, but that we want to have the ability to plan maneuvers and autonomously control on board, which is potentially very useful to achieve the science objectives of a mission like advisors, because the spacecraft have very stringent position velocity marks that they have to hit in order to take the observations that we need, and this kind of necessitates onboard planning and reacting to the current state estimate. So these will be algorithms for doing onboard planning of maneuvers and onboard safety analysis of the formation. So a key issue we face in the advisor's propulsion system is it's an impulsive propulsion system, but it's very limited in the magnitude and the frequency of the maneuvers it can output. By frequency, I mean like how often you can maneuver, not like the frequency or duty cycle like of a valve firing. It's like there's a refill time of the plenum that will be exerting the gas that actuates the system. So that is a pretty severe limitation in the large relative state reconfigurations we have to do to get from our very safe standby mode, which the spacecraft will be in when they're not taking observations, to our science mode. In the standby mode, we have nominal separations of hundreds of meters, but in the science mode, we are in the tens of meters range. And then there's a large transition between them, in which the closed form algorithms we have, which are we've implemented some slab homegrown algorithms for optimal impulsive control of the relative orbit state, but they do not have guarantees on the size of maneuvers that need to be output. So we have these nice closed form solutions that we want to be able to use on our small constrained platform. And how can we do that? So I'll introduce some algorithms for taking in a original maneuver plan, which will be a series of impulse velocities at specific times, and outputting a maneuver plan that will accomplish the same state, relative state configuration, but while abiding the constraints on the delta V and the time between maneuvers. So we'll start with an analytical approach. So this is an example, or this is the control input matrix for an impulsive velocity on the ROE state. And you'll notice that in the terms controlling particularly the relative eccentricity and relative inclination vector, that's these last four terms, we have lots of sinusoidal, and this is in a near circular orbit, chief reference orbit. We have which is characteristic of visors. We have these sinusoid terms, which give us some symmetry. So never mind, everything's correct, I think, which give us symmetry in the dispersion or in the spread of maneuvers around a location. So if we were to say have an ideal maneuver location and we were to maneuver 10 seconds ahead of time and 10 seconds before that, we could cancel out the off-optimal effects of those maneuvers and achieve the same, or the off-desired effects of these maneuvers, and achieve the same desired reconfiguration with a series of maneuvers that are all constraint abiding, but not no single maneuver is violating the maximum constraint. And so visualized here, so rather than achieving this large single delta V, we achieve with a series of small delta Vs. And we achieve a reconfiguration of the relative eccentricity inclination vector and the relative symmetry axis and delta lambda. In this analytical framework, this is the algorithm for achieving that, which basically just iteratively adds maneuvers of the same magnitude spread symmetrically in fixed denominations of the minimum refill time of the plenum to achieve the original state reconfiguration using control abiding maneuvers. So it is an iterative algorithm where you need to, you don't know ahead of time how many maneuvers you need. You just add maneuvers until you reach the number that you need, and then you can achieve the same state reconfiguration that you needed. So this is an example where the blue trajectories are, this is a step in our transfer between science and standby modes. And in the eccentricity, and this is in like the three major ROE planes, the eccentricity plane, inclination plane, and the relative symmetry axis delta lambda plane. And we can see the straight blue lines are what a nominal two-step in the normal direction impulse, and three steps in the tangential impulse, and then 3 steps in the three steps in the ellipsometer axis are then achieved with these slightly offline following red series of maneuvers. And the accumulation of the difference, you could, or like an optimal maneuver will be straight along a line basically in these planes. But these optimal maneuvers accumulate a bit of area between the solution and the optimal solution, and that contributes basically an inefficiency to the solution, which here you can see is a 97% efficient solution. So compared to the delta V you would have to use to do this, if you had the fuel optimal solution, you can do this 97% efficiently with this algorithm. You may note, though, that in this algorithm that I introduced, you are decomposing maneuver by maneuver to make sure each maneuver from your original plan is broken up. However, this doesn't guarantee that maneuvers that happen in your original plan don't collide in this decomposed space. So you could have 2 maneuvers that you split up and then they run into each other, and then you're violating your time between maneuvers, and then you're violating your control constraints. So in the case that maneuvers decompositions overlap, we can introduce an optimization problem to pose a linear program using linear dynamics of the relative state to accomplish the same ROE state transition as desired, but with control abiding maneuvers for the entire reconfiguration. And the way this is achieved is it's a linear program that basically minimizes the delta V's, the L1 norm of the delta V's. That's these terms contribute to doing, it's called a basis pursuit problem. It's a pretty standard linear program formulation. And then when we constrain the velocities to ensure that we abide by constraints is the instantaneous 1 norm basically of the positive direction RTM velocities along like 6 axes from the RTN frame of the spacecraft have to be less than the total, and the dynamics have to be satisfied in which over a window of time around each original maneuver, the state transition, which is you can use a linear, there are many linear state transition matrices for the relative state, abides to reach the final desired relative state. So that is the algorithm, how it works at its part, and then you need to, in the case that maneuvers overrun each other, you can simply combine the original maneuvers in the dynamics equation to create a joined maneuver that is then composed. So the original plan looks like this. I don't know if you guys can see the mouse well from where you're sitting, but the top left, the original plan is this. You decompose your maneuvers into this first extended plan. The decomposition runs into each other for that red and that green maneuver. The red and the green maneuvers dynamics are then combined, and the optimization problem is rerun so that the resulting decomposition abides by constraints for every single maneuver.
Like the issue there is that you have like green and red just lower than the mean inspiration on the second line.
Yeah, yes. So in this one, like these maneuvers, the time between them is less than the refill time. So you would need to, so that plan would not be physically possible with the actuator system. In which case you can just combine the propagated dynamics linearly in the constraint equation and rerun the optimization. It's a linear program which runs quickly. I should note that Visors has an embedded conic solver on board for its science mode control, which is what allows us to trivially accomplish this, because a linear program is a subset of second order cone program, so it is trivially solvable by the solver we have on board, assuming that it works every time. If it doesn't work, we fall back to using the analytical solution with larger spread out maneuvers. But linear programs are efficiently solved, and they're also give guarantees if you can find a solution, it is the optimal solution. The onboard solver we have is a interior point solver, though not like a simplex or a dedicated linear program solver. So if you included a dedicated linear program solver, you'd probably have better checks of feasibility and give that faster than our solution. But this is already going on by there, so it's a handy little addendum. And you can see that this solution is slightly less fuel efficient than the previous one, and the 93% efficiency versus the previous one was at 97, but that's because the previous one was kind of cheating because it had the decomposition of maneuvers running into each other. That was actually not a physically acceptable trajectory, but this is a truly constraint abiding trajectory. So you do lose some fuel efficiency, but you are, of course, able to actuate your plans. And now into the safety violation prediction. So you can have a few different paradigms for your safety of your distributed space system or any autonomous system, and these can be passive, proactive, reactive. A passive system, passively safe system, is one that follows a trajectory that does not require further control inputs at any moment to maintain safety between the elements for some time horizon. Or the reactive one would mean where you have to, at any given time, if a contingency is detected or an unsafe scenario is detected, you would have to maneuver immediately to rectify it, or when it is, or rectify it before you collide or violate your safety. A proactive system is somewhat in the middle, where you are on a trajectory that where you ensure that your control trajectories can be escaped from efficiently or with the reduced control capability, so that you could potentially find yourself only on trajectories which you could escape from with a single maneuver if you needed to. But for most of the Visors mission, and I would guess many distributed spacecraft missions, we have a passive safe orbit design by design using eccentricity inclination vector separation, which gives us separation in the RN plane, which tends to be pretty stable with respect to perturbation effects and uncertainty. So in order to monitor the robustness of the margin of passive safety, we use a algorithm that checks basically the margin from the between the spacecraft between the chief spacecraft and a confidence interval around the deputy spacecraft. And the way this is done is at instance of receiving state updates of the relative state between the spacecraft, the deputy and chief spacecraft states are propagated, the absolute states with Gauss variational equations over some horizon, and then the covariances of the relative state are propagated linearly using linear state transitions. And then at each instance or time step along the propagated trajectory, we compute a distance in the RN plane and the RT plane separately to this confidence interval of states of the deputy relative to the chief in Cartesian space. And there's a transformation between the ROE space to the Cartesian space covariance, which is a linear transformation. And this allows us to say not specifically a probability of the spacecraft colliding, but a probability that the spacecraft maintain a minimum distance. So instead of directly estimating the collision probability, we are guaranteeing a minimum separation threshold over this horizon. And a violation of this threshold is what we consider a passive safety violation rather than an instantaneous violation of the separation. And so during the nominal operation of the Visors formation, this is showing, and also this happens separately in the RN and the RT planes. The RN is checked first because it is supposed to be stable and lower uncertainty. In the RT plane, you do have elongation, particularly along the T direction of the uncertainty ellipse. And it may not give as good results, but depending on the orbit, the absolute orbit that we're injected into, Specifically for visors, we may not be able to guarantee passive safety just on the RN plane. So it would be nice if we could, but that's not a guarantee. So we have to nominally check both planes. Otherwise, we'll trigger violations all the time, and that would deplete the fuel reserves of the visor's mission rapidly, and we would burn out before we could take observations. But we in this we see the actual true separation between the spacecraft in the simulation framework that we have, and the predicted minimum separation threshold over a time horizon up to 3 sigma confidence interval on the 2D ellipsoids, or the 2D ellipses in the RT and RN plane. And this is just showing the RN plane ellipse, but it is always lower than the true separation between the spacecraft. This has only been really tested in cases where the violation is not happening, because we can put the spacecraft on a violation trajectory where we know they're going to get too close together, but we do not yet have simulations where, say, a control failure happens or the state estimation wildly degrades that causes a actual like emergency. So we can contrive emergencies where they are going to crash into each other because we can set the original states, but I have work to do to actually robustly test if in the case that control uncertainty leads to, or like the thrusters fail, stay open, lead to huge degradation of the relative state inclination vector separation, how that affects these solutions. But that is the methodology behind these systems of visors and what they will do to protect us and make us flight capable. That is all.